Good afternoon, everyone. I'm Bob Keating. I'm a solution architect at NVIDIA, and today I'll be talking about the Holoscan, NVIDIA Holoscan for domain-agnostic AI-enabled sensor processing. First things first, this is how you get started with the hands-on lab. So I recommend starting that up now so that it's ready to go when we get to the hands-on lab portion. I'm going to talk about Holoscan for about 15, 20 minutes, and then we'll get into the hands-on lab. So just go to learn.nvidia.com/DLI-event. If you don't have an NVIDIA developer account, you'll have to create one. They're free. And then you log in with your developer account and enter the NVIDIA XLab OC24 code. You may also want to test that WebSockets works on your browser. We have a link here for that, websocketstest.courses.nvidia.com. We do recommend the Chrome browser. If you have Chrome in your system, that's preferred. So I think hopefully everyone's got their environment up and running. If you're having any troubles, please put a message in the chat and one of our teaching assistants will help. So once you start your lab up, you'll get to the screen. You'll want to click on the Start button in the lower right corner there, and that will start the virtual machine environment. Notice the slide deck here. You can view the slide deck here, but you can also download it. There's a little menu in the lower right-hand corner of the slide viewer, and if you click on that, you'll get a menu and you can download this slide deck locally, so you'll have it. Once your virtual environment is up and running, you'll see this screen. You'll click on the Launch button, and that will open a new browser tab that will have your hands-on lab environment. Okay, if anyone has any problems starting your environment, like I said, please use the chat and someone will help. So I'm going to start into our presentation, and so businesses from all industries are striving to incorporate AI-driven insights. Efficient and timely processing of these AI-driven insights relies on compute resources being close to the sources of data. In the case of sensor-driven workflows, like we see in medical imaging a lot, we also see them in retail, manufacturing, logistics, and safety industries. This is best accomplished through edge computing. Benefits of edge computing for sensor processing include real-time insights by locating processing power close to sensor data sources. Second, extending data center intelligence to the edge can accelerate real-time actions to be taken while transmitting useful insights back to the data center for additional processing. Thirdly, cost savings due to reduced quantity of data needing to be transmitted and stored for additional processing. And then finally, enabling software-defined sensors to manage and reduce the cost of high-resolution sensor processing. So this leads us to what NVIDIA has defined as 4 pillars of edge computing. First is real-time insights, where you have processing power close to the location of sensors, enabling real-time insights. These locations could be warehouses, shopping malls, science labs, hospital beds, imaging centers, or operating rooms. Generating real-time insights close to the point of data generation saves time, adds efficiency, improves productivity, and in the case of healthcare, can improve quality of care. Secondly, intelligent edge AI. AI intelligence at the edge serves as an extension to the data center intelligence. It enables faster and more efficient sensor processing, reducing the time from data acquisition to insight, which is really important for healthcare use cases. Thirdly is cost savings. The ongoing increase in number of sensors and sensor resolutions makes it essential to keep costs down by processing sensor data at the edge. This reduces the data transmission and storage costs. And then finally, new tools. Intelligent edge systems will require businesses to rethink their data center workflows and computing infrastructure. They'll need new tools supporting transition to an operation of intelligent edge systems to stay competitive in their industries. So let's take a look at the anatomy of a typical sensor processing pipeline. So we've got a kind of what we think is a common processing pipeline depicted here. The first is a pre-processing step that takes raw sensor data and processes it to implement signal conditioning and data transformation needed for subsequent processing. That gets passed into an AI inferencing step where AI algorithms may be applied to produce real-time analytics. Thirdly, there's post-processing where you would apply domain-specific data processing and transformations. And then finally, visualization. AI augmented results are rendered and displayed to the operator. These processing pipeline steps may apply regardless of the industry or problem domain. They serve as a foundation for building AI-enabled sensor processing pipelines for all industries. The Holoscan SDK was developed to abstract away the complexity of building these pipelines, improving time to market, and reducing maintenance cost. This shows how edge computing is an extension of the work done in the data center and cloud. Data center and cloud computing resources work together with edge computing to keep AI-based analytics up to date at the edge. Data from the edge can then be fed back to the data center or cloud for continuous learning so that models can be continuously improved and kept up to date with local data characteristics. Let's take a look at the details of Holoscan, which is NVIDIA's AI-enabled streaming sensor platform. At the heart of the Holoscan platform is the Holoscan SDK, which supports building pipeline processing applications in either C++ or Python. These applications can be multi-node and multi-GPU, supporting multiple AI inference backends. Holoscan applications can scale from IGX Orin and Jetson Orin, which is our embedded systems, to x86 systems, including OEM workstations and DGX systems. IGX and Jetson systems are ARM-based and are available from multiple NVIDIA embedded partners. The Holoscan platform provides benefits including simplified sensor I/O to GPU data transfer, simplified deployment of AI models, customizable and reusable components for building GPU-accelerated applications, scalable and distributed computing, and deployment to cloud and cloud-native systems using the container-based app packager. Let's go through some fundamentals of the Holoscan SDK. We'll start with the software stack. The base layer is composed of CUDA and Vulkan. CUDA, as I'm sure many of you know at this point, is the GPU accelerated computing toolkit from NVIDIA, and Vulkan is a GPU accelerated visualization API. Next, there's TensorRT and libtorch for AI inferencing, and then GXF, the graph execution framework. GXF is a core framework for design and execution of GPU accelerated compute graphs. But for ease of programming, the Holoscan SDK provides its own foundation layer for simplified access to GXF. This is done in the form of directed acyclic graphs of operators. These operators have defined inputs and outputs, which are connected into compute pipelines executed by the GXF engine. Built on top of these core components are pre-built operators, a C++ layer for defining your own operators and composing and running pipelines, and a Python layer for ease of prototyping and experimentation. The Python layer will be used in the hands-on lab today, but there's also an optional C++ content that you can complete on your own if you're interested in that. Finally, the software stack is completed with availability of a comprehensive and growing set of community-driven sample apps and pre-trained models. Next, let's dive into details of operators, the core Holoscan SDK building block. Core Holoscan operators are provided for I/O, compute processing, visualization, and AI inferencing. Holoscan extensions add capabilities to the core of the SDK, such as support for bare demosaicing from imaging sensors, and OpenGL for rendering, in addition to the core Vulkan renderer. Custom Holoscan operators are a very important part of the SDK. They allow developers to wrap their custom functionality or software libraries in Holoscan operators. We'll see examples of this in the hands-on portion of the course. This allows the SDK to support application or domain-specific tasks across a wide range of functionality, ranging from I/O to computation, reporting, and visualization. Custom operators integrate seamlessly with existing GPU accelerated libraries. So all of the rich CUDA ecosystem set of libraries can be used with Holoscan operators. And they can be combined easily with core Holoscan operators. Sample operator designs are available showing how to define the number and type of inputs and outputs for your custom operators, as well as defining the processing they perform. We'll see how to do this in the hands-on portion of the course. The next fundamental I want to talk about is scalability through distributed computing architecture. As I previously mentioned, Holoscan applications are defined as a directed acyclic graph of operators. These graphs can also be defined as multiple fragments. So being shown here are two fragments. These fragments can be defined to execute on specific GPUs, and in this case, we're running on GPU 0 on a node, and then the second fragment is running on GPU 1 on the same node. Data movement within a fragment is done efficiently using GPU pointers. So in this case, if you're running on the same node, there would be no copying of data. The pointers would be exchanged between the fragments very efficiently. If you're running between separate nodes, then it would use the Unified Communication X, or UCX, which is an optimized point-to-point communication framework standard. Next, the Holoscan SDK includes profilers and schedulers, allowing your applications to be optimized for best execution performance. In addition to NVIDIA's powerful Nsight performance profiling and optimization tools, the Holoscan SDK adds data flow tracking, so you can track data latency as packets or frames move through the Holoscan application. Holoscan 2.5 adds support for detailed profiling of Holoscan applications using the Nsight Systems tool. To help optimize graph execution for different types of processing, multiple schedulers are also provided in the SDK. The greedy scheduler, the default scheduler, uses a single CPU thread to launch operators in a sequential pipeline. The multi-threaded scheduler allows operators to be pinned to specific CPU threads and enables asynchronous execution of the operators in pipeline parallels, and we'll get to see that in the hands-on portion as well. And not shown here, there's a new scheduler, which is the event-driven scheduler, which provides application control, very detailed application control of operator execution. And finally, interoperability and portability are provided through multi-backend AI model-to-app capability and an application packager and runner. Model-to-app provides a plug-and-play model-to-application building capability, and the app packager and runner use container technology to package and run applications for ease of deployment across multiple platforms. This is through building something called a Holoscan application package, which was modeled after the Monai application package design. To help you get started with designing Holoscan applications, NVIDIA has created the HoloHub GitHub repository of sample applications. HoloHub provides a diverse and growing collection of collection of sample Holoscan SDK applications. They can be used as starting points to create your own applications. They include applications such as sensor I/O, AI sensor processing, GPU accelerated sensor processing, and more. You can use the links provided here to access the HoloHub GitHub repository and the sample applications folder. This isn't in the downloaded slides you'll get from the lab, but I've also added a link here to a specific sample application, which is the Monai endoscopy tool segmentation sample application. This uses the Monai model zoo endoscopy tool segmentation model. So based on this application, it should be fairly straightforward to start from the sample application and integrate your own pre-trained models from a Monai bundle. And then finally, here is a summary of helpful resources to get you started with the Holoscan SDK. The main, I should mention the Holoscan SDK is open source, so you can find the source code on the GitHub repository shown here, the Holoscan SDK to GitHub. But it's also easily installed by pulling a Docker container from NVIDIA's NGC container repository. You can install it in your Python environment through pip install Holoscan. And there's also Debian packages available for package manager install. You can learn more about it using the SDK user guide at the NVIDIA documentation hub. So thanks for your attention. Now we're going to move on to the hands-on lab portion. Hopefully everybody has their hands-on lab environment running. I'm going to switch over to that environment. So once you have started your lab environment, so you'll click on the launch button, like I had mentioned before, and that'll open your Jupyter Lab tab on your browser. Now, I'm not going to go through this. This is the same content that I just covered in the slide presentation, so I'm not going to go through this in detail. You can read that at your leisure. But I will go through the course structure. So what we're going to do in the hands-on portion is we're going to learn how to create custom Holoscan operators, how operators connect to form an application, how to build Holoscan applications with GPU accelerated Python packages, how to build a sensor to visualization pipeline, how to leverage core operators that come packaged with the Holoscan SDK, such as the AI inference operator, which is a very powerful one, a little complicated, but with some time spent on learning it, you can get a lot of work done with that one. How to measure and optimize application performance, how to build complex sensor processing workflows using multiple fragments like we had discussed, and also using the multi-threaded scheduler. And then how to package a Holoscan application for deployment for cloud or other compute architectures. There is a C++ notebook. If you're interested in doing the C++ portion, you can do that on your own. It's very short, but the majority of the time we'll spend today is on the Python. So now open the notebook 2, and this is the main Python Holoscan tutorial. So our first Holoscan application, we're going to define a pipeline of 3 operators. We have a ping TX op, a ping middle op, and a ping RX op. So the transmitter, a middle processor, and then a receiver. Each of these has, so the ping TX op is we're calling that a source, a data source. It has no inputs, and it has 2 outputs. The middle operator takes 2 inputs, does some processing, and then writes that to 2 outputs. And then the sync at the end, which is the ping RX op, has no outputs and only 2 inputs. So the ping TX op is going to generate some data. It's going to run it through the pipeline for processing, and then the ping RX op is simply going to print some information. So to get started, first thing we're going to do is we're going to load the operator and operator spec classes from the Holoscan core. And so the operator is the most basic unit of work in the SDK. You're going to receive streaming data at an input port, process it, publish it to one of its output ports. An operator can have multiple input and output ports. Each input or output has a unique name. Let's see what else we talked about that. So now we're going to look at the code for defining the transmit operator. So I'll run this code, and this defines a Python class called pingtxop. It's derived from the Holoscan operator base class. And you see it has an init method, a setup method, and a compute method. So the init method is a function that's used to initialize any class-specific parameters. And then, of course, it calls the operator base class init method. The setup function is used to define your input and output ports. And then the compute function is actually what's called as the schedule executes your operator and actually performs the processing on the inputs and outputs. A little more on the setup function. So this comes from the operator spec base class. To create an input port, you use the spec.input method and you provide the name of the port. To create an output port, you call spec.output and give it the name of the output port. The compute function, so this takes the place of the operator's compute functionality. As you can see, the example above, the compute function allows the three separate parameters to be passed in by default to the function. We'll focus on op input and op output. So you can see here the compute takes the self object, op input, op output, and context. Receive data from an upstream operator. So this coming into the input of the operator, you use the op input receive method, providing the name of the port. And that'll retrieve the value of that input and assign it to an object. To write to an output, you use the emit method of the op output object, also providing the name of, in this case, the output port, and providing the value. So now we have our first exercise. So we've got some familiarity now with the building of custom Holoscan operators. So now you're going to define your own operator called myOp. So it's going to have the following. It's going to have 3 input ports named in1, in2, and in3, 2 output ports named out1 and out2. And in the compute function, you'll always emit the data received on in1 to the out1 port, and then you're going to emit into to the out2 port if the operator tick is odd, and in3 to the out2 port if the operator tick or if the tick is even. So there's a little hint here is to use self.index. So we're basically going to create an index member variable on our operator class, and that's going to be initialized. And then every time we call the compute function, we can increment that, and you'll be able to check whether that's even or odd. So I'll give you a few minutes to write that code. Just note that anywhere where you're writing code in a cell below it, there will be a click here to view the solution. So if you're stuck, you can just click that link and it'll open a tab with the solution to that exercise. So I've copied the solution into my notebook here. You can step through that. If I'm going too fast, please put a message in the chat. But in the interest of time, I wanted to keep things moving. Um, so we see here we're declaring a class called myop. It's derived from operator. Defines an init method that, as I mentioned, is going to create an index member variable and initialize it to 0. And that's really all it does. And then it calls the parent class init method. Then the setup method is going to define our inputs, which are simply in1, in2, and 3, and then outputs out1 and out2. The compute method is going to retrieve the value of in1 by calling op input receive. It assigns that to in1 value. Then it's going to call op output emit. That's going to write the in1 value that it retrieved to out1. That's pretty straightforward. Then we retrieve the values of in2 and in3 using the receive method. Now we're just going to you're going to use the modulus operator to check if the tick count, which is an index, is even or odd. If it's even, we'll emit in2 to out2. If it's odd, we'll emit in3 to out2. And then we increment the index. So hopefully that was pretty straightforward. If there's any questions, please put them in the chat. Now we're going to create a custom middle operator for our example here. So the ping middle op, this is the code that is defined for the operator that was described. I see a question, what is the utility of the index parameter? So the index parameter in this example is simply here as a counter to count the number of ticks. And a tick is it's a scheduler time increment. So every time the scheduler ticks over, it's going to execute any operators that are ready for execution. So this is going to count the number of times basically this operator called myop has executed, and then we're going to use that to see if that count is even or odd. So this is a local variable that's stored with the instance of the operator called myop. So you can instantiate multiple myop operators. Each one will have its own private index count. I should mention, so this code is not available on GitHub, but you will have access to this lab for some period of time after today. Just be aware that the lab will take a little longer to start up. It'll usually take 5 to 10 minutes to start the environment up after today, but you will have access. It's typically for 6 months. I don't know what the duration is for this class, but you will have access to the code later today, and you can download the code from the file browser. So on the left-hand panel here, there's a file browser that you can use to download all of the code locally. So you could run this locally on your own system. But this is not yet available in GitHub directly. What is value data doing in the ping TX op? Let's go back up to that. So yeah, value data is actually don't know that. It's the first time anyone asked about that. I think this is just a data type conversion. we'll talk about data types a little further down. That is one of the trickier parts about Holoscan is if you need to convert any data types between inputs and outputs, and we'll cover that further down. Okay, so this custom middle operator, so this is the one that's in the middle of that original pipeline that we talked about. So it's got a counter. It's defining much like the index. This one is calling a count, so it's going to count the number of times this is executed. In the setup method, we define 2 inputs, 2 outputs, and then you'll see something new. We have a spec.param multiplier. So multiplier is going to be used in the compute step. Here, we're going to multiply the input values by the multiplier. And we could have defined this as a local member variable in the class, but this is just showing you how to take an alternate approach. You can define parameters that are read in from a config file. So each operator can be associated with a YAML, an external YAML configuration file, and you can put parameters. There's a number of things you can do in there, but one of the things you can do is define parameters associated with an instance of an operator. So in this case, we're going to read the parameter. If we had a config file, we would read the parameter multiplier from the config file. But if you don't have the config file, this second parameter here, then the integer 2 here defines the default value. So it'll be a parameter with a default value 2, and it could be overridden by an external config file. Okay, so now we have the custom sync operator. We'll get to, there's an example further down showing how to set an external config file. We'll get to that. So the ping RxOp, this is the sync object. So we see it has, again, something a little different. Now we have, instead of defining an input method using the input, like we did up here using the spec.input, here we're using spec.param, and we're giving it the name receivers, and there's a parameter called kind, where we're setting kind equal to receivers. So that, as it's described in the text here, this is a way to accept a dynamically sized input. So this input can have any number of inputs connected to the operator. And we'll see further down how we can use that. So we've defined these 3 operators now. We've got the ping RxOp, we've got the ping middle op, and we've got the ping TXOP we defined up here. So now how do we create, we've just defined the operators. We haven't created an application yet. So how do we create an application? So we're going to need something else from the Holoscan core and Holoscan conditions. We haven't talked about conditions yet. I'll talk about those. So we'll import these 2 packages. And then we're going to define a new class. This is the application class. So my ping app is derived from the Holoscan core application base class and has one method called compose. So in compose, that's where we actually instantiate the classes that we defined. So we're creating instances of ping TXOP and ping MX, or ping middle op, and then ping RxOp. And when we instantiate them, we get to provide names. We can set conditions. We'll talk about the condition in a minute. And then right here, this is where we can see from config. So when I instantiate the operator, I can put this from config in here. Okay, and it's going to load from a config file. So now we've instantiated our operators, but they're not connected yet. So they're connected by using the add flow method of the application class. So we're going to add a flow. In this case, we're going to connect the transmit and the middle objects or operators, and we're going to connect out one and in one and out two and in two. And then we have a second flow where we're connecting the middle operator with the sync, the receive operator, and we're going to connect out one to receivers and out two to receivers. So you see here the way that we're using the dynamically sized single receivers input. So it's going to send out one and out two across from the middle operator to the sync, the RX operator, as basically a tensor of two items. Okay, so the count condition. So conditions could be very useful. They're a way to modify the execution behavior of an operator. So a condition could be a count condition where it's going to set the number of times, the number of ticks basically that the operator is going to execute for. It could be a Boolean condition, so you can set the value of the condition at runtime to enable and disable dynamically the execution of an operator. And then message available conditions. So you can set, instead of an operator running every time the scheduler has a tick, this says, okay, only run it on a tick when there's new data available. So if I don't say this, the default is the compute method is going to run every time that operator is invoked by the scheduler. If you set message available condition, then it's only going to run when there's new data available on its inputs. So conditions are potentially very, very useful. So now I'll run this cell, and this will define our application class. Now to run the application in your Python script, you're going to, this is some sample code here. It's going to load an environment log level. This is just to set the log level for the application. It's going to create an instance of the application class. And this is where you can load, again, from your config file. In this case, the config file is called ping.yaml. So there's a file in the file system here called ping.yaml. And it's going to load any configurable parameters from that file and apply them to the operators in the pipeline, in the application. And then you run it. So this is already in this ping.py file, so we can run ping.py by executing this cell, and we see the output. So we've executed this whole pipeline. So that brings us to exercise 2. Exercise 2 is it's your turn to write some code. So there's a file in the file system called pingpow.py. You're going to edit that file to create a new operator called pow2 on 2. So pow2 on 2 is going to square incoming integers if the clock tick is even. So you're going to use that local variable, that local counter variable to count clock ticks again and check if it's odd or even. If it's odd, you're going to pass through the data directly. You're not going to square it. So you're going to need to edit the pingpow.py file, and you can do that by clicking, or you can view the solution here, where you can open pingpow.py from the file browser here. If you look at the Python folder and go to exercises, you can see you have pingpow.py. So I can edit this file in a new tab. And if you scroll down, you see the to-do item here. So this is where I'm going to create a new operator. Okay, I'm going to do it by subclassing from operator, and I'm going to call it I'm going to call it POW2 on 2. And then I'm going to implement this behavior that's described here. And then don't forget to modify the application definition, the compose method in the application, to use the POW2 on 2 instead of the middle operator. So I'll give you some time to work on that. And if you have any questions, use the chat. Yeah, that was a good point in the chat. Thank you. So you can open if you go to File, the File menu in the Jupyter Notebook, you can do New and create a terminal window, or you can run it from a cell. But once you get into the terminal window, you could create a tar file and compress all the files up, and then you can download that file using the file browser. Good point. Thanks, Anas. If you want to ask a question verbally, you can come off of mute, and you can raise your hand in the chat or in the yeah. Okay, so so one way to do this is how to execute this. If you copy all of the code from the pingpow.py, you can paste it into this cell and execute it. So that's the easiest thing to do in this case. So here's the solution I'm showing you now. So we've defined a new operator called pow2 on 2. Oh, and as mentioned earlier, here's the class value data. That's the user-defined data type that was referenced earlier. So pow2 on 2 is going to define a counter, a local member variable counter to count a number of ticks. Then in the setup method, we define in1 and in2 inputs, out1 and out2, and then there's still that multiplier. In the compute method, we're going to receive in1, we're going to receive in2 into local variables. We're printing some messages out for debugging. And then we check if the count is even or odd. So if the count is even, okay, we're going to multiply value 1 data by itself. So we'll square it and square value 2 data. And then we increment the counter. And then we emit both value 1 and value 2 out, outputs out 1 and out 2. And then we had to modify in the application class right here. So the middle operator, the MX operator, is now pow2 on 2 instead of the MX middle operator. And then we execute it. Yeah, I've got some error messages here. I've never seen those before, but there might be something wrong with my environment. So the other way to run it is to just save the changes in pingpow.py, and then you can just execute this cell. Oh, but I didn't make the actual changes, so it's going to fail. So that's the other way. So I've copied the solution file into pingpy or pingpow.py, and then you just execute the file with the Python, the bang line here. Or as Bogdan said, yes, you can open a terminal and you can run it in the terminal. So there's some options. But the easiest, I think, is if you just edit the file by double clicking on it in the browser, make your changes to the file, save it, and then you just execute this cell to run the application. So the next section here is about how to run Holoscan applications or build Holoscan applications with GPU accelerated Python packages. So this is a very powerful concept to learn. What's more, the advantages of Python, it has such a rich collection of packages, and many of them have GPU acceleration capability. All of those can be used within Holoscan operators. So what we're going to do here is we're going to do a Fourier transform using CuPy's FFT function. So we'll import CuPy as CP. Then we're going to create a new operator by subclassing the Holoscan operator class, and we're going to call it FFT op. Nothing special in the init function. It has an input called time in and has an output called frequency out. In the compute method, you can see here we're going to call op input receive and assign that to sig. So that's our time domain signal input. And then we call CuPy FFT with the signal tensor. And then we're going to emit that. So we're actually doing this all in line here. So this is going to return a tensor that then is going to be the first parameter to the emit function. So we'll emit the return value of CuPy FFT to the sig out output of the operator. So now we've got our operator defined. That brings us to exercise 3, where you're going to create a Holoscan application that consists of 3 operators, a source op that emits 3 ticks of random arrays of size 32,768 samples, then the FFT operator that we just defined, and then a sync op that prints the results of the FFT operator. So you click on the file here, fftapp.py, to open a starting file that you can insert your code into. So we're going to create a source op. You can copy over the FFT op code, and then you're going to create a sync op, and then define your application. So we'll give you probably about 10 minutes for this one. It's a little bit more work. Well, it's been about 10 minutes, so I think we should move on. So I have the solution on the screen here. We're defining a class called sourceOp. It has a single output called out. And in the compute method, it's going to emit CuPy, the output of CuPyRandom.ranDN. So we're using an external package to incorporate the functionality. So this will generate a tensor with random data values and write it to the output. Then we're going to have the FFT operator, which is copied from the one in the write-up. So that's pretty straightforward. So we're going to call the CuPy FFT operator function, passing in the input, which was the output of the source op, which is the output of CuPyRandom.ranDN. And then we define a sync operator, which has a single input, and it's going to take that input and it's just going to print it. Then we define the application. We instantiate the source operator, we instantiate the FFT, we instantiate the sync operator. And then and notice that the source operator does have a count condition, so it's only going to run for 3 iterations. Then we connect them by adding flows, connecting source to FFT, and then connecting FFT to sync. And we instantiate the FFT app. Don't just use the default configurations, and then we do app run. So we can run that by executing this run application cell here, and we see the output. So we do have a challenge exercise here. I'm not going to go through that in detail. But it's to include a source op that emits 5 ticks of 1,000 by 10 random values, updates with each tick along with a 1,000 by 1,000 random value matrix that doesn't change. And then it's also going to do a matrix multiplication operator and a sync operator. So that'll be left to do on your own time. The next section is using pre-built Holoscan operators. So as I'd mentioned in the presentation, one of the advantages of Holoscan is it has a large and growing collection of um, built-in operators. So we're going to build an application here. It's going to be totally composed of built-in operators, and it's going to be an AI-guided ultrasound bone scoliosis segmentation application. So the basic workflow for this is it's going to use a video stream replayer. This is a built-in operator. So this is really useful because it allows you to read video from a file. So when you don't have a real sensor, and you can stream that into your pipeline. The format converter is a good one to learn. It has a lot of powerful operations. So this one is going to convert from 8-bit integer to FP32, and it's going to resize the image. Then we're going to pass that into an inference module. It's going to perform segmentation, and then we're going to pass it into a segmentation post-processor that's going to convert the results from the segmentation model output to a format needed to visualize it in the HoloViz visualization component. And then we pass it into HoloViz, and it shows the inference results. So here's the code for that. We can define everything, but unfortunately we can't run it in this Jupyter Notebook environment because HoloViz is going to try to create an X11 window, and that doesn't work. It would actually try to display it, I think, on the server. So we can't run it in this Jupyter Notebook. You can download all the files and run it on your own system and see it in live action, but we do have a video here that we can play. So if you downloaded this code and ran it on your own system, this is what you would see. So we can see that the segmentation, which is the output of the inferencing operation, is being overlaid with the input video, and it's being displayed by HoloViz. So this is something we haven't done yet, right? So it's not a simple straight through pipeline. So HoloViz has the ability to take two inputs and it will overlay them, right? So the output of the segmentation post-processor is going to HoloViz, and the output of the video stream replayer is also going into HoloViz. So that's how we get the two streams overlaid. And we do that just by simply adding multiple flows here. So we have the segmentation visualizers connected to segmentation post-processor in this last step, but it's also connected to the source up here. So that's how we get two inputs going into the visualizer so we can get that overlay capability. Next, we're going to talk about tensor interoperability and combining custom operators with core operators. So this is where things are getting a little trickier because we're dealing with different data types requirements for different operators. So an operator receives a stream of data on an input port. It processes it and publishes it to one of its output ports. The operators included in the SDK provide domain agnostic functionality such as I/O, machine learning, and inference processing and visualization. They're optimized for AI streaming pipelines. When assembling a C++ application, there are two types of operators that can be used. There's a native C++ operator and a GXF operator. When assembling a Python application, there are two types of operators that can be used. There's native Python, and then there are Python wrappers of C++ operators. So we're dealing with different data type representations in those cases. So this section is going to describe how you can convert between these different data representations. So the first one is to see how to read a Holoscan GXF tensor object into an operator and convert it into a CuPy array. So this is converting basically between what would be used by the C++ wrapper object and a native Python operator, custom operator. So the way to do that is in this compute method, we're getting the op input and the op output objects. We're going to receive the input tensor, in this case, into a local variable called the in message. And this is then going to be a dictionary that has a set of key value pairs. So we can loop through the keys and the values in message, and then we can convert each value to a CuPy array using CuPy's as array function. So this is how to get basically if you're getting data from a built-in operator, which would be a C++ wrapper, this is how you would convert it into a format that could be input into a custom Python operator. Now, this is going to convert each item in this dictionary into CuPy arrays, but it's not really doing anything with it. So if we knew the name of the item that we wanted, you can retrieve them by name. So in this case, we're receiving a specific key value from the input tensor by using the in-message get method. So we're retrieving the input into in-message, which gives us the whole tensor, or the whole dictionary. And then we're using the get method on that object to retrieve a specific piece of a data item by name. And then we can convert that to a CuPy array. So to convert a CuPy array to a Holoscan GXF tensor, so this is going the other way, so I can take a custom Python operator and send its output to, say, a built-in Holoscan operator. Here's an example of that. So we're receiving an input tensor, and we're creating a new an output variable, and we're declaring it as a dictionary. And then we loop through the keys and values in message.items. And then we're going to convert each one to a CuPy array. And then we're going to build this out message by appending each CuPy array for each item to the message with its key value. So we're building our own dictionary here. And then we're going to do op output emit, out message, and output tensor. So that brings us to exercise 4. Build a custom operator that accepts 2 tensor input streams from a core Holoscan operator at the custom operator's ports, input 1 and input 2. We'll only want to convert 2 tensors with the names original value from input 1 and current value from input 2. We're going to convert them to CuPy arrays and take the difference of the 2 tensors, regardless of which other tensors may be present in ports in input 1 and input 2. We're going to emit the results from an operator with knowledge that the next in the application pipeline is also a core Holoscan operator. Okay, so we're combining the pieces that we just saw here. So we're going to retrieve data items by name using this method. Okay, and we're going to convert them to CuPy arrays, and then we're going to build a dictionary with the outputs and then write them to the output of the object with this method. So we'll give you another 5 minutes. We'll see how things are going. Let's go over the solution to this exercise. So I've got the solution here. So it's pretty straightforward. It's like I said, we have defining our operator, and we're taking our input from the receive method. We're getting the specific item name by key name and putting that in one tensor. And then we're converting that to a CuPy array using CuPy as array. And then we do the same thing with the second input using the specified name current value. We calculate the difference because these are just CuPy arrays now, so it's pretty easy. And then we define the out message dictionary and add each of these items by name. And then we output the message to out. Actually, it's just, I'm sorry, it's the difference. So we add the difference that we calculated by name. So this becomes a dictionary with one item in it called diff, and then we output that using the emit method, and that can then be passed into a built-in operator. So the next section is putting it all together with an object detection with an SSD model. So this is getting into a little bit more about different ways you can use the inference operator, which is a very powerful operator to learn. In this case, we're using a YAML file, so a YAML config file that will configure all of the parameters of the inference operation. So we're taking a lot of that complexity and putting it in that YAML file, and then when you actually go to instantiate it in your application, it's much simpler. That's one nice tip about the inference operator. We've got some sample code here that's doing the detection processing. So here's a full real application. And again, this is using the visualizer, so we can't display it interactively, but I can show the video. So this SSD model example is actually performing this inferencing on the video frames as they're coming in. So you can see the kind of the advantage of a Holoscan with its low latency streaming processing abilities. So now we're going to get into optimizing your application. I mentioned the data flow tracker. It's a performance tool that is part of Holoscan. It's very easy to use. So when you instantiate your application object, and then you go to execute your application, you can use the tracker here. So you basically execute your application with the tracker, and then the tracker will automatically, perform the latency tracking, and then you can simply do tracker print to print your results out. You can also specify a file name to say where the log output goes. And just simply calling tracker.print will print all of the tracking flow results into that log file. So the next section is on scheduler selection. Again, selecting the scheduler is pretty straightforward. You create the scheduler here. It's an object or class, so you create an instance of the scheduler that you want, and then you invoke the app.scheduler method to set the scheduler, and then you just run your application. So we can see here an example if we run multiple type counts of threads. So when you instantiate your multi-threaded scheduler, you can specify how many threads you want, how you want deadlock behavior to be performed, what the timeout is. So if there's any potential for a deadlock to occur using multiple threads, you can have a safety valve for that. Basically, it'll get you out of that deadlock. But you can see here in this case, if I run this example model here where I'm just running a bunch of delays and I'm running them in parallel with the multiple threads, you can see the latency reduces dramatically as I increase the number of threads that I'm using. So it goes from 752 milliseconds with 8 threads down to 242 with 32 threads. I'm not saying you're always going to see that performance, depends on the application, but it's definitely something that could be very beneficial. So yeah, you can, the next exercise, this is just sort of a try it out thing. So you want to try out the multi-threaded scheduler. So you can run this existing Python file here with different parameters. So just play around with it. I won't pause on this one, but you can try it on your own time and try different numbers of threads. Try tweaking the delay operations. You can see how if you put in 0 for the number of threads, it's going to use the greedy scheduler. So you can just play around with different parameters and see how the two different schedulers behave with different characteristics of your processing pipeline. The next thing is the distributed applications, where we create fragments. This is pretty straightforward. There's a fragment base class. So you create an instance of, or you subclass from the fragment base class. So I've got here a class called fragment1. Okay, and fragment1 has a compose method. So it's kind of like similar to the application class somewhat. So you're creating a fragment of an application, think of it that way. And then in your application compose method, you can link the inputs and outputs of your fragments. So in exercise 6, you can modify my ping app to split the operations into two segments, into two fragments. So I'll give people 5 minutes or so to work on that one, and then we'll continue on. We're almost done. So I've got the solution up for this exercise. You can go through it. The thing you'll notice, so it's a pretty simple, kind of a nonsensical example. We have each fragment has one operator in it. So because of that, you'll notice a difference from the example up here. The example up here, we're instantiating operators, adding them to the fragment using the add operator method, and then we added a flow between those two. So we have a fragment that has two operators in it that are interconnected. So the outputs of the inputs and outputs of the fragment are the inputs and outputs of the kind of the ends of that pipeline, that fragment. Because these are single operator fragments, we didn't need to add a flow. So it defaults to the output of this fragment is the output of the TX operator, and the output of the second fragment is, I'm sorry, the input of the second operator is the input of the RX. So RX has no output and TX has no input. So this is a very simple situation. And you see we used add flow here. So we instantiated the two fragments in the application, and then we added a flow connecting the TX and RX fragments. This line here is showing how you could use a config file to configure your fragments. So this is where if you wanted to get into specifying an alternate node or a specific GPUs that these fragments were meant to run on, you could do that from the config file, the YAML config file. We'll run that. That didn't work. I think I skipped some includes. So moving on, so the application packaging, this is one that we can't really demonstrate here. You can't run it because it's actually building a container. And this whole notebook environment is running in a container. So we couldn't really implement the app packager. So this is something that you have to try by downloading to your own system, and you can try it there, but it's pretty straightforward. There's a Holoscan package utility. So you run Holoscan package with some parameters, and it will build a container from your application. And then to run it, there's a Holoscan run command. So it's pretty straightforward. You can try that on your own. So for more examples, like I'd mentioned, there are a lot of examples on HoloHub. So please go and check them out. Exercise 7 is for you to think up something interesting and write your own Holoscan application. Hopefully you know enough now to be able to put together an application that may do something a little more meaningful in your own problem space. So that brings us to the end of the Python section. The only other thing I wanted to show was briefly the C++ notebook. If you're interested in the C++ part, this is a much shorter notebook. So all of the concepts are similar. It's just C++ APIs instead of Python.